Thank you for taking the time to have a look at this video. I've been interested in hexaflexagons for some years, and I particularly enjoy creating hexaflexagons beyond the standard ones you see in many videos. However, there seem to be few resources that show how to create more complicated hexaflexagons, so I created an algorithm that allows me to build any hexaflexagon I want. I thought that I might share this in case anyone else finds it useful. First, a quick overview to answer the question, what is a hexaflexagon? Very generally, a flexagon is formed from a strip of paper that can be folded and then flexed in such a way that different faces show. The two most common types are tetraflexagons, which are formed from squares, and hexaflexagons, which are formed from triangles and look like a hexagon when the strip is folded. It is the latter that we're looking at in this video. From now on, if I refer to flexagons rather than hexaflexagons, you can assume that I'm talking about hexaflexagons. A very useful tool for analysing hexaflexagons is the Tuckerman diagram, named after Brian Tuckerman, who created it, I believe, in the 1940s. This diagram shows how the faces of the flexagon relate to each other as you flex the flexagon. Here on the left we have a diagram for the simplest hexaflexagon, the tri-hexaflexagon. The two numbers on each node show which numbered face is showing on the top and bottom of the flexagon respectively. Of course, any flexagon can have either side uppermost, so it's arbitrary which side of the flexagon is top and which bottom, so we just choose one side as top and stick with it. By the way, in this video I'm using numbers to distinguish the faces. Of course, you can have letters, colours, fancy designs, whatever your imagination comes up with. However, we're just going to keep it simple and use numbers in this video. So, we can see from the diagram that if you were looking at face 1 and flex, we go to face 2. Then another flex takes you to 3, and then another back to 1. We've now visited all the faces of this flexagon. If we are flexing the bottom side, we will use the same diagram, but we'll be moving in the opposite direction to the arrows. Now, on the right we can see the basic strip from which the flexagon is created. And here's its other side. Each basic strip will have as many triangles as there are faces for the flexagon, in this case 3. A hexaflexagon is always created from 3 of these basic strips stuck together, as we can see here. Note that the second of these strips, i.e. the middle 3 triangles, is reversed. The bottom side is showing. This is always the case for hexaflexagons with an odd number of faces. For hexaflexagons with an even number of faces, each of the 3 basic strips has the same orientation. If we want to build a flexagon with 4 faces, we just need to add another triangle to the diagram. We can do this on any of the original nodes. However, you can see that the shape of the diagram is essentially the same for each choice. It's the overall shape of the diagram that separates flexagons of different type. As all the choices for where to add the extra triangle are the same, there is only one hexaflexagon with 4 faces. We'll cover exactly how you determine which numbers appear in each node shortly, but notice that we now have a face 4. Each time we add a triangle to the diagram, it gives us a diagram for a flexagon with 1 additional face. So, we now have the diagram for the 4-faced hexaflexagon, also known as the tetrahexaflexagon. Note that this has 2 triangles in the diagram, 2 less than the number of faces. This is always the case. So, for instance, a hexaflexagon with 9 faces will have 7 triangles in its diagram. Notice that for this flexagon, on the face labelled 2, we can flex to 2 different faces, either from 2 to 3 or from 2 to 4. On the right is the strip that the tetrahexaflexagon is created from. You'll notice that it isn't straight. In fact, only hexaflexagons that have a number of faces divisible by 3 can be formed from straight strips. If we add another triangle to the diagram, we get the diagram for the 5-faced hexaflexagon. Again, although we can add the triangle to any node which has only one path in and out, all the resulting diagrams are essentially the same shape, so there is only one type of 5-faced hexaflexagon. This changes for the 6-faced hexaflexagon, the hexaflexagon. There are 3 different 6-faced hexaflexagons. The first, which is the most common hexaflexagon that you're likely to come across, is this one, which is formed from a straight strip. The other 2 are not formed from straight strips. Because these diagrams have fundamentally different shapes, each is counted as a different flexagon. If we continue adding triangles to the diagram, we get diagrams of flexagons with progressively larger number of faces. There are 4 with 7 faces, 12 with 8 faces, and so on. So, our next task is to devise an algorithm that will allow us to create any hexaflexagon that we want based on its diagram. We'll approach this in 2 main steps. First, creating the relevant diagram, then using the diagram to create the strip from which the flexagon can be constructed. We're going to try building one of the 7-faced hexaflexagons. You'll remember that the diagram for any hexaflexagon has 2 fewer triangles than there are faces, so we'll need a diagram with 5 triangles in total. We'll start from the diagram for the simplest 3-faced hexaflexagon. Let's add the first triangle to the 2-1 node, like this. Notice how the arrows pointing out of the 2-1 node are opposite each other, and likewise the 2 arrows pointing towards the node. Let's think about how we get the correct numbering for the faces. Whenever a new triangle is added, the top face for the first node will be a new face. We'll label this as 4. The bottom face will be the same as the bottom face of the node pointed to by the opposite outward arrow. In this case it's a 2. So our first node will be 4, 2. For the second new node, the top face will be the same as the top face for the opposite node, similar to what we did for the first node, but using the top rather than the bottom face. In this case, it's a 1. The bottom face for the second new node will be the new face number, i.e. 4, so the label for this node is 1, 4. Now we'll add a third triangle, this time to the 3, 2 node. You might like to pause the video and, using the rules for the previous new triangle, see if you can work out what the new nodes on this triangle will look like. Well, here it is. The first new node has top face 5, the new face number. The bottom face is 3, the same as the bottom face for the 1, 3 node, opposite the 3, 2 node. The second node has top face 2, the same as the 2, 1 node opposite, and the bottom face 5. Now we'll add a couple more triangles using exactly the same rules. First to the 2, 5 node, and then to the 5, 6 node. Okay, we now have 5 triangles in the diagram, so using the rule that a flexagon has 2 more faces than it has triangles in its diagram, we have a diagram for a 7-faced flexagon. We now have to construct the strip that can be used to make the flexagon. We'll do this using the following algorithm. First, there are a number of choices to make. The algorithm should work whatever you choose for these, but I'll show the ones that I normally choose. Choosing the same ones each time just makes the process a bit simpler. The strip we want to construct is made up of a series of equilateral triangles, so I'll add the first triangle. Initially I'll leave it blank. We'll add the relevant text to the face very soon. I always add this first triangle with its base facing down. Next, choose a starting side for the triangle. I always choose the bottom side. Then we add an orientation to the chosen side. This will seem a little mysterious to start with, but hopefully the method behind the madness will become clear in due course. I normally choose a clockwise orientation, as shown by the arrow. So, we're going to construct the strip by working around the nodes on the diagram, hence we need to choose a node to start from. We can start wherever we like, but I tend to choose one of the nodes with only one path in and out. Let's choose the 6, 7 node. We also need to choose whether to start using top or bottom labels. We'll start using top labels. Again, why we're doing this should become clear very soon, but it will change as we go through the procedure, so we need to keep track of this. We now iterate around the edge of the diagram, stopping at each node with only one pair in and out arrows. Importantly, we count the number of lines we pass on the diagram. Whether that number is odd or even determines where the next triangle in the strip will go and what number appears on each triangle. So, starting at the 6, 7 node, we follow the arrows around, passing the 5, 6, 2, 5 and 3, 2 nodes until we reach the next node with a single in-out arrow, the 1, 3 node. That's 4 steps. Now, if the number of steps is even, we choose the face number to be the same as for the previous node, i.e. top or bottom. Remember that we chose to start using the top labels, so we can add the top number from the 1, 3 node as the label, i.e. 1. The face number for the reverse of the triangle, which of course we can't see at the moment, will be the second label, in this case 3. If there had been an odd number of steps, we would have changed whether we're using top or bottom for the labels. We'll see this again shortly. We also need to get the orientation of the labels correct so that they appear symmetrically on the completed flexagon. As for the other choices we've made, this can be arbitrary to start with, but after choosing the first orientation, the rest are all determined. Let's choose this orientation for the label text, pointing to the bottom right corner of the triangle. The label on the reverse side points towards the same corner. There are now 2 empty sides to the triangle, so we need to determine which one we will use to continue the strip. If the number of steps is even, as we have here, then the next triangle will be attached to the side that the previous arrow is pointing to, so it will be attached here. If there had been an odd number of steps, we would have added the new triangle to the left-hand side, i.e. the opposite side to which the previous arrow was pointing. Also, if the number of steps is even, we add an arrow between the existing and new triangles with the same orientation as the one previously. In this case, it will be clockwise. If it had been odd, we would have changed the orientation and added an anti-clockwise arrow on the left-hand side. At the end of each iteration, you should have this pattern where there is a blank triangle and an arrow between it and the previous completed triangle. We now just repeat these steps until we get back to our starting point on the diagram. So, the next node with single in-out arrows is 4, 2 node. That's 2 steps, so an even number again. As it's even, we continue using top for the label, so this will be 4. The opposite side, which we can't see, will be 2. For the orientation of the text on the label, the rule is that if we can make the label text point to the same corner as the previous triangle, we make that the orientation. If we can't do this, we make the orientation point in the opposite direction. In this case, we can make the text point towards the same corner as the previous triangle. We now need to add the next triangle. As the number of steps is even, we add this to the side pointed to by the previous arrow, like this. We also need to add the next arrow. Again, for an even number of steps, we add an arrow with the same orientation as the previous one. The next node with single in-out arrows is just 1 step away, the 1, 4 node. As 1 step is odd, we change to using the bottom label, i.e. 4. 1 will be on the reverse side. For the orientation of the text, we can make it point towards the same corner as the previous label. An odd number of steps also means that the next triangle will be added to the side that isn't pointed to by the previous arrow, and we change the orientation of the arrow to anti-clockwise, like this. At this point, you might like to pause the video and try to predict where the next triangle will go and what the new label will be. This time there are 3 steps to the 5, 3 node. As this is odd, we need to change the label choice, in this case from using the bottom label to the top label, i.e. 5. 3 will be on the reverse side. Notice that we can't make the text point to the same corner as the previous triangle, so we add it pointing away from the previous triangle's text. As the number of steps is odd, we add the next triangle to the side not pointed to by the previous arrow, like this. We also need to add the next pointer, and because the number of steps is odd, we change the orientation to clockwise. And on we go. Pause the video at this point if you want to check your understanding by predicting what happens next. Well, it's 2 steps to the next node with single in-out arrows, the 6, 2 node. That's even, so the face label will be staying on the top face, i.e. 6. For the label orientation, we can make this point to the same corner as the label on the previous triangle. The next triangle will be attached to this side and the orientation of the next arrow will stay the same, clockwise. 2 steps again to the 7-5 node, so the labels will be the same as previously, i.e. top, so a 7. The next triangle will be added here, and the arrow will have the same clockwise orientation. The next iteration is just 1 step, so odd. The label will therefore change, in this case to the bottom label, a 7. The next triangle will be attached on this side, and the orientation of the arrow will change to anti-clockwise. We've now got 7 triangles on the strip. The flexagon we are constructing has 7 faces, so this is as many triangles as we need. The full flexagon will be constructed from 3 copies of this strip. Note the orientations coming into and leaving the strip. This tells us how each partial strip joins to the next strip. You might find it helpful to leave a tab on these 2 faces when you create the physical strip, which can be very helpful when folding the flexagon. Another tip if you're struggling to see how the next partial strip joins is to keep iterating around the diagram a second time for a few triangles. These extra triangles will show how the next strip joins to the first one. Also remember that for hexaflexagons with an odd number of faces, the middle partial strip is turned over, and here you'll see that the middle 7 triangles, highlighted in yellow, are reversed. So now we just have to fold our strip to form the final flexagon. Do this one type of face at a time. So for instance, in this case we might fold the 3 pairs of 7s. A good guide for whether each set of folds is correct is that at each stage, after folding one set of faces, the resulting strip should be symmetrical. When you've done a few of these, you might also notice that at each stage of the folding process, you create a strip which is identical to a strip with 1 fewer face. So for our flexagon, after folding over the faces labelled with 6, we get this shaped strip, which is the same as the strip for the 5-faced hexaflexagon, and so on. I often find that the trickiest part is connecting the 2 ends once the flexagon is fully folded. In particular, for this flexagon it might be tempting to attach the face labelled 1 to the face on the other side, the 2. However, this would be wrong. The 1 face needs to be attached to the face labelled 6, which is in between the 1 and 2 faces. Again, having a tab on the faces that need to be connected is very useful. Now that we've completed the flexagon, let's check that it matches the diagram. Notice that the labels on the faces appear symmetrically. This is the result of how we oriented the labels when building the flexagon strip. Note that when we turn the flexagon over, we move through the diagram in the opposite direction to the arrows. Okay, looks good. So that's how I create my flexagons. Obviously there are a few steps to the algorithm, but I don't think any of them are particularly difficult. It's just a matter of being careful and keeping track of the orientation and whether you're using the top or bottom faces for the labels. Here's a summary of the steps for creating the flexagon strip. Thanks for making it through the whole video. If you try this method to make your own flexagons, let me know how you get on in the comments. And if this has been helpful, please give it a like.